I'm going to show you how to make this animation. We're going to remake the animation parts of it. I'm going to skip some steps, but I'm going to go over everything. And this comes from the question, how is it possible that momentum can be conserved but not kinetic energy? So let's run this animation and then we'll talk about that. So here I have a yellow ball colliding with this other thing I made. I mean, when I made that, I was just like visually attracted to it, and I love it. So let's talk about why it would be confusing, and then we'll come back over to the code, and we're going to make this code, and I will give you the code. You will have the code, and you can do whatever you want with the code and use it in your class or not use it in your class. Okay, so paper time. So suppose I have two objects that are colliding. So I have object A, it's moving towards B, and B's at rest, just for fun. B's at rest. And so it has an initial momentum PA1, meaning initial. And then it collides. That's my symbol for later, sometime later. And then they both move. Who cares? It's something. I mean, I care. We all care. But they're both moving. If we define momentum as mass times velocity, and if we have no external forces on the system, then the change in momentum of the system has to be 0. So the momentum before has to be the momentum afterwards, and we can write that as the following equation. MAVA1, mass velocity B, all that stuff. Okay, well, if kinetic energy is 1/2 mv squared, and they both depend on mass and velocity, how can the kinetic energy not also be conserved? So should not 1/2 MAVA1 squared scalar plus 1/2 MBVB1 squared is not necessarily equal to MAVA2 squared plus 1/2 MBVB2 squared. And I'll go ahead and tell you the short answer, and that's why I made that animation. If B has some internal structure, like I replace B with two masses connected by a spring, then the center of mass of this will have the same momentum as that, but it may not have the same kinetic energy because the internal energy takes away some of that energy. And I think it's really easier to see in the animation. So let's just jump back to the animation and build this code. So let me go over the important parts of the code, because it's important to understand what's going on. If I have two balls, A and B, and this one doesn't have any internal structure, how do I make a collision? Well, one way, the way that I want to do it, is to say, well, if these two balls overlap, so let's imagine that here's A, and it's overlapping with B a little bit. In that case, I'm going to say there's a force, this is of A pushing on B, and then there's a force push of B pushing back on A that's proportional to this overlap. And we can say FA on B. I can calculate this vector from here to there. I'll call that R. And then I can say F is going to be equal to, if they overlap, negative KR. I think I can say it like that. So the more they overlap, the greater the force they push apart, and it doesn't even matter. As long as these two forces are equal and opposite, then momentum will be conserved. And that's not too difficult to do. I mean, you have to have some if statements in there, and we're going to do that. Now, in this other model, what I have is I have object A, and then here I have object B is actually two masses. So I split it into two, and I connect it by a spring. Now, I can do a collision just like this for this mass and this mass. And I just realized I'm calling, in my code, I call this B. Why did I call that B? And these are A1, and this is A2, and that's B1. I'm sorry. It doesn't really matter, though. So I can do a collision between these two just like that. If they overlap, there's a force pushing them apart. And then this I can call some unstretched length, L0, and this is a different spring constant, much weaker. I want this to be a strong spring constant, K, so that it's a stiff collision. And this is weaker so that we can see it oscillating. But we can change that up and see what happens. And then, so the force on this, if I call this the vector L from A1 to A2, then the force on A2, I'll call that F internal, it's going to be equal to negative the other K. So let's just call this, K2. Let's call this K of the unstretched length L0. I'm looking at two things. Unstretched length negative K, unstretched length L0 minus the magnitude of that length L times L hat, right? Because, so what this is going to do, this is the amount it's stretched or compressed, and this L hat turns it back into a vector. The L hat is a unit vector in the direction of L. And the negative sign means it's if it's stretched, it pulls back that way. And then I can find the force on this one. It's just the opposite of that. So this one can have 0 or 1 force on it, be an interaction between that one. This one's going to have 2 forces on it, the interaction with this plus the spring, and this one's just going to have the spring. And then I can calculate the center of mass, just put it right there. So I can say R center of mass is going to be equal to M A1 times the position RA1 plus MA2 RA2 over MA1 plus MA2. And so I can calculate that. And then what I did, I'm going to put a sphere around that just so it looks like it's one object. Okay, it's a lot of stuff to work on, and let's jump right into it. Okay, we're done with this. Okay, so let me go over it. Let me run what I have, and then I'm going to show you all the code I have, and then I'm going to finish the program. So this is it running. So all I did was I didn't animate anything. I just made the object. So I have this I'm calling B1. This is A1, A2. That's the center mass. And it's in 3D, so you can rotate it around. And I'm going to show you all the parts of this code, and I'm going to give you the code, so everyone should be happy. Okay, so let's just go over all this stuff. This stuff right here, I was going to retype it, but this is just stuff to make a graph. I'm actually making 2 graphs. I'm going to make a graph for the momentum of everything and the kinetic energy. And so we'll talk about that later. I just didn't want to have to type it. So B1 is the yellow object. It's a sphere. I put it at a value of x equals -1. I give it a radius, a color, make trail, all that stuff. R is the radius of my big circle, right? My squishy ball. And it has 2 masses, A1 and A2. So I made those. One's at negative, it starts at the origin. One's at -R, one's at +R. And they both have a smaller radius, and they're different color. Now I'm going to give everything a mass. So if I want those 2 objects to have equal masses, the squishy ball, and the non-squishy ball to have equal masses, then I need to divide that mass into 2 pieces. So B1 has a mass of 0.1. AM is the total mass of the other object, so I just divide it by 2. They're equal masses. They don't have to be. You could have it whatever you want. And I'm using here, in case you haven't seen, once I make the sphere B1, I can give it a attribute mass.m. So that means I don't have to worry about all these mass variables. I can just say B1.m. It's actually really useful when you have more than 3 things. Okay, this is the initial momentum of everything. I need to have, if I'm going to update momentums, and I didn't show you that, I need to have the initial momentums. I need the initial positions and the initial momentums. And let me just remind you really quickly, in case you haven't seen the 8 billion videos I made, and I'm not offended, that's cool. I'm going to show you the very, very simple numerical method that we can use to calculate the motion of these things. So switching back to paper really quick. I apologize for that. I should have said this before. Where's my pen? Okay. So once I calculate the force on an object, the net force, by whatever means is needed, I can say F net is the change in momentum with respect to time. And I'm going to break this into super short time intervals. Let's say delta t is 0.001 seconds. And during that time, I can assume the force is constant. If that's true, then I can say P2 is P1 plus F net delta t. So I can take the initial momentum calculate that force, multiply it by dt, and find the momentum at the end of the time interval. Then I can do the same thing by assuming the momentum is constant and calculate the new position. And I get this. R2 is R1 plus P2 over M delta T. And then I can update time. T2 is T1 plus delta T. And then I go back up here and do the whole thing again. That's the plan, right? But I need to calculate all these forces. And if this is like, whoa, I've never seen that before, just let me know in the comments down below. I'll post a couple of my favorite videos that go over this in vast amounts of detail. Okay. But that's really, I'm making this program as a demo. It's a demo program, not really a calculation program. Okay, next thing. We're down here. R com is the vector location of the center of mass. So it's the vector location of A1, which is A1.pos, times its mass, plus the vector location of A2 divided by the total mass. That's the definition of the center mass. And then I use com, center of mass. It's an actual object. It's a sphere. It doesn't really have any forces acting on it. It's just to display something. And so it's at the location of the center mass. Give it a radius and a color. That's that red dot. And then the spring is, you don't even have to put the spring. I just want to draw the spring so you can see it. There is that helix in Web VPython. I need a position is the location of one side of the spring. Axis is a vector from one side to the other. The radius is the thickness of the coils, or the whole thing. And then the thickness is the thickness of the wire. And this AA is my sphere to represent the squishy object. So I make it as a sphere of radius R. I made it a little bit bigger so it encloses the things. And then you can make it transparent with a value, a property called opacity. And so opacity of 1 would be not transparent, and 0 would be completely transparent. So I'll put 0.3. For the springs, I have the spring constant and the squishy object is K. And so L0 is the unstretched length. So it's whatever they start at, they're not stretched. So I'm going to pick those two positions and say that's my unstretched length. And then I give a spring constant of 10 newtons per meter. And then the colliding spring constant when the B1 overlaps with A1 is 100. Times 0, dt is 0.01. Okay, so let's do this. I want to make a loop. I like time loops. So I'm going to say while t is less than 4. So this will run for 4 seconds. I need to give a rate statement here. So rate 1000. So rate 1000, what that does is it says don't do more than 1,000 loops per second. And with a time step of 0.001, this would run in real time. So you can change this to make it run faster than real time. You can change it to make it run slower than real time, whatever you want. I want real time. Okay, so the first thing I want to do is to calculate the vector location from A1, that left ball, to B1. And I need to use that so I can see if they're overlapping. And if they are overlapping, I can calculate the force. So let's say RB1. This is the vector from B to A. It's going to be equal to A1.pos minus B1.pos. It's from B to A. It's that vector. I'm sorry. Yeah, I always get the video backwards, you know. Now I'm going to do this. FB1 is vector 0, 0, 0. So FB1 is the force on object B1. And I set it to 0. Because every time I go through the loop, I need to say, are they overlapping or not? If they're not overlapping, then I need to have a 0 force. If they are overlapping, I'm going to have a force. But every time I'm going to start with a 0 force and then say, if it's not 0, change it. So let's see if it has to be changed. So I would just say if the magnitude of RB1 is less than the distance between the centers of those two spheres. So that's going to be equal to B1 dot, let's see, B1 dot radius is the radius of B1 plus A1 dot radius. And you can actually have any value that you want. It doesn't really matter what value you have for when there is a force and when there's not. As the only key thing is they have to have the same and equal and opposite forces. That's the only key thing. So if that's true, then I can calculate FB1 as negative K2 times RB1. RB1. And so that is a vector. That's a key thing to remember. That is a vector, right? Because RB1 is that vector distance between those two. And if it's not, then it stays a zero force. Okay, what is next? I need to now calculate the vector between A1 and A2. So I need that for the spring. So let's say L is the vector A2.pos minus A1.pos. So it's that vector from one of the squishy masses to the other one. And I need that to calculate the spring force. And let's call that internal, F internal, because it's my internal force. And it's going to be equal to negative K times L0 minus mag L times norm L. So norm returns a unit vector for that vector. Now I can assign forces to each object. And this is something that I like to do when I have complicated situations. So let's say this, B1.F is the net force on mass B1. And that's just going to be equal to FB1, right? That's the only force that could possibly be on B1 is that. And it's going to be either 0 or some value. A1.F is going to be equal to negative FB1 because if A1 pushes on B1, B1 pushes back, and so it should have that same force. And then it has this internal force due to the spring, F int. And then A2.F is just going to be negative F int, right? It's the negative of that internal force. So now I have all three forces, net forces on the three objects. I can use those to update the momentum. So let's update the momentum of all three of these objects. So B1.P equals B1.P plus B1.F times et. A1.P equals A1. You gotta when you say this, you gotta say it out loud and you gotta enunciate. You gotta say A1.P. If you don't, it's not gonna work. Your code won't work. Now watch my code not work. A1.P plus A1.F times et. A2.P. And you could put this in a list. You can do more complicated things, but if it's just 3, I don't really think it's worth it. Okay, so that updates the momentum of all three objects. Now I need to update the position of all three objects. B1.pos, B1.pos, plus B1.p times dt divided by B1.m. So remember, B1.p divided by B1.m is the velocity. I could just copy that, but it doesn't take too long to type. P1, A1.pos plus A1.p times dt divided by A1.m. A2.pos equals A2.pos plus A2.p times dt divided by A2.m. Boom. Okay. Now, I do have some more work to do, right? Because there's some other visual elements I need to adjust. That would move everything, but I want to recalculate the center mass, move the center of mass, move the sphere, move the spring. So I got to do all those things. The first thing let's do is just to calculate the center mass. I did that up here, so I'm going to recalculate that because the positions all moved. So I need to recalculate the center mass. Now I can move the center mass. Com.pos is com.pos. I'm sorry, is rcom. Right, I'm just going to move it. The next thing I want to do is to move the sphere. So aa.pos, it's also going to be centered at the center mass. Now I need to move the spring. So I'm going to move, remember my spring was connected to A1 and went to A2. So spring.pos is A1.pos. And then spring.axis is going to be A2.pos minus A1.pos. Okay, that should move the spring. And then did I update time? I did not update time. Update time, t equals t plus dt. I think that's going to work. Let's save it because you never know what's going to happen with this stuff, right? And I am giving you the code. I told you that. Okay, now for the moment of truth. I give myself a 92% chance of working. Nice. Pretty happy. Okay, so I did this as a head-on collision because that's the one that's easiest to see. And it's amazing that it works with an off angle, and I'll do that later. But let's go ahead and see if momentum is conserved and if kinetic energy is conserved. Let's just do momentum first. So up here, I already made a graph, momentum versus time. I made 4 curves. FB1 is the momentum for the x momentum for mass 1. FA2, FA1, the 2 momentums of the 2 masses, and then the total momentum. So I want to plot those 3 things, and I'm forgetting them. We're at FB1, so I'm going to come down here to plot. I'm just going to say FB1.plot T B1.P.x. You can't plot the x you can't plot the momentum because it's a vector. So I have to plot the x component of the momentum. FA1.plot T A1.P.x. FA2.plot T A2.P.x. And then the total, what did I call that? FT? FT. FT.plot T, and let's just add this up, which I didn't have to do. B1.P.x plus A1.P.x plus A2.P.x. Okay, let's run it. Okay, so starting off, both of the balls, the springy balls, are red curves, so they're both red. The total is purple, and the yellow one's blue. I feel like that trailer from Guardians of the Galaxy where they're trying to figure out the buttons. It just came out, and that's what I have to think, but whatever. So you'll notice that the total momentum is constant. That's cool. And the ball that's moving slows down and drops down here, and then the other 2 balls oscillate. But they have momentum, and some of their momentums makes the total work. So the momentum works. Everything's great. I'm pretty happy with that. Notice that some of these have, nope, they're always positive. They're always positive momentums, and that's fine. So that's pretty cool. I'm pretty happy with that. Okay, now let's do the kinetic energy. So the kinetic energy, I already made graphs for that. So in Web v Python for graphing, if you want multiple graphs, you can say which graph you want each curve to go with, but if you put them in order, it works and it's much easier. So if I put G1 as graph 1 for the momentum, G2 is the graph for kinetic energy, and then the curves below that are fine. Now these I'm going to forget. I'm going to copy all these because I'm going to forget the labeling here. I do need to calculate the kinetic energies. So let's put this down here. And these are not. I'm just going to say dot plot. Dot plot. Just so I won't forget. I just forgot the names of these, and I just don't want to. Because that's what I do. I make mistakes. So I can get rid of that. Get rid of that. Okay, so I need to calculate the kinetic energy. I didn't ever calculate the velocity. So I can calculate the kinetic energy as momentum squared divided by 2m. Okay, now I've got to take the magnitude of the momentum first. So let's do that right here. K B1. It's going to be equal to B1 mag B1 dot P squared divided by 2 times B1 dot M. KA1 equals mag A1 dot P squared divided by 2 times A1 dot M. Oops. And then KA2 equals mag A2 dot P squared divided by 2 times A2 dot M. And then in the total, KT equals KB1 plus KA1 plus KA2. And now to plot it, I'm going to say time, and B1 is KB1. Case matters, be careful. Plot this one. TKA1 dot plot TKA2 dot plot TKA2 K total. Let's see if it works. Okay, looks like it's working. Okay, so this is the kinetic energy, and you'll notice it is not conserved. Not conserved, because here's my purple for the total. It comes down here and it drops down and it oscillates. The total kinetic energy is not conserved. Pretty cool. And so we can think of the total kinetic energy not being conserved because there's another term in there. There's another energy term in this problem, and that's potential energy. I have not included the potential energy of the spring. If you include the potential in the spring, then the kinetic energy is indeed conserved. Now, what I'd really want to do is to plot the kinetic energy of the center mass. Let's do that instead. Let's plot the momentum of the center mass and the kinetic energy of the center mass. Let's not plot the two masses individually. So I need to calculate the momentum of the center mass, and I need to do that. Let's do that first. Okay, so down here, let's calculate the momentum of the center mass is just the velocity. We can calculate that as the velocity of the center mass times the total mass, or it's just the weighted average of the center mass. Yeah, so let's say P total is going to be PA total, but not pat. Okay, it's going to be A1 dot P parentheses A1 dot P. No, it is just the sum of the momentums. Is that not right? Yeah, it's just the sum of the momentums. PA1 plus A1 dot A2 dot P. Yeah, that's the total. And then the total kinetic energy, Ka total, is going to be equal to mag PAT squared divided by 2 times A1.m plus A2.m. I'm pretty sure that's true. Okay, so down here for the plotting, I'm not going to plot FA2. I'm just going to turn FA1 into this, and it's going to be PAT.x. And I don't have a value for that. It's just a vector value, PAT, so I only need the x component. And then down here for the kinetic energy, I'm not going to plot the second kinetic energy. I'm going to plot this. Let's count this. Oh no, I want to calculate that. I'm plotting it. I don't want to plot the second one. And let's just plot this as, what do I call it? Cat. Yeah. Now the total momentum, let's plot the total momentum up here as PB1 plus pat.x. Yeah. Okay, I think that should work. Okay, it's colliding. Okay, momentum's conserved. And then this shows that kinetic energy is not conserved, just like we said, and that's pretty good. Okay, I'm pretty happy. One more thing, and that's what I made in the original video. So how I can make a glancing collision pretty easily. All I have to do is shift up mass B, so when it collides, the force between them is at an angle. And I'm not going to do anything with angular momentum because it gets pretty complicated. Not too bad, but so all I need to do up here is to shift this up just a little bit, 0.02. I'm going to pick 0.02. So it's 0.02 in the y-axis, so it's not going to hit head on. And so both of the things move off at an angle, and my squishy thing spins. So it has rotational kinetic energy too. I mean, you don't have to split it up as rotational kinetic energy. And I wouldn't, because since it's springy, it doesn't have a constant moment of inertia, so it's kind of complicated that way. But still, you can look at the total energies. Here's the momentum in the x direction, and here's the kinetic energy. Same thing still works, and so that's kind of cool. Let's make this one more. Let's make it a little bit more glancing. So let's try 0.3. Okay. I think that's the one I had in the original video. And you can try changing the masses. You can try changing everything. And it's just fun. So like I said, I will give you a link to the code down below. This is in Trinket, which is implementation of WebVPython. If you click on the code, you can edit it and run it, and you don't even have to log in. To save it, you're going to have to log in. But I don't mind if you use this for your classes or whatever, because it's fun. I had a great time making it. So that's that, and I will talk to you later.